Good morning, everyone. Today, I'm excited to present our final year project titled A Deep Learning Approach for Classifying AI-Generated Art versus Human-Created Artwork. I'm presenting on behalf of our dedicated team from the Department of Electrical Engineering at NFC Institute of Engineering and Technology. Our team consists of Derek Shinamanzara, our group leader, along with Bakhtiar Hussain, Bisma Ali, and Furqan Tahir. This project has been supervised by Ma'am Terry Maywan. Project Overview and Table of Contents. Our presentation today will cover several key areas. First, we'll establish our research area and domain within computer vision and deep learning. We'll examine our specific area of interest in AI-generated versus human-created image classification. Next, we'll outline our project objectives and goals, followed by a comprehensive literature review of current research in this field. We'll then walk through our systems block diagram and workflow, and finally discuss our hardware and software requirements. Research area and domain. The research domain of our project operates within computer vision, a branch of artificial intelligence that enables machines to understand and analyze visual data. Specifically, we employ deep learning techniques to identify patterns and make predictions regarding image origins. Our scope focuses on the classification of AI-generated art and human-created images using deep learning models. Research gap and problem statement. Our research addresses several critical gaps in current technology. Many existing fake image detection methods rely heavily on metadata and watermarks. But these approaches fail when dealing with AI-generated images that don't contain such features. The number of available models that focus exclusively on visual content patterns for classification remains surprisingly small. Additionally, comprehensive comparisons between deep CNN architectures for distinguishing human-created from AI-generated images, beyond facial recognition applications, haven't been thoroughly examined in existing research. Most importantly, there are no systems currently available that provide both scalability and real-time functionality suitable for social media platforms, journalism, and digital forensic applications. Project objectives. Our project has four main objectives. First, we aim to create an equally distributed dataset of human-made and AI-generated images with proper labeling. Second, we'll process these images through resizing operations, normalization, and RGB format conversion to prepare them for deep learning applications. Third, we'll implement feature extraction using multiple convolutional neural network architectures. Finally, we'll compare their performance to identify the optimal model for real-world deployment. Understanding images and pixels. Let me explain what we're actually working with. An image represents visual information that can include simple drawings, photographed pictures, recorded graphs, or any similar content. It contains visual information in the form of light intensities and colors. Common image formats include JPEG, Joint Photographic Expert Group, PNG, Portable Network Graphic, and GIF, Graphic Interchange Format. At its core, an image consists of millions of small elements called pixels. A pixel is the smallest unit in a digital image, and multiple pixels arranged in rows and columns form the complete image we see. Each pixel contains either intensity values for black and white or grayscale images, or color values for full color images, typically in RGB format. Our CNN models analyze these pixel arrangements and patterns to learn the distinguishing characteristics between AI-generated and human-created artwork, AI versus human images. Understanding the difference. The fundamental distinction lies in their creation process. AI-generated images are produced by advanced deep learning architectures including CNNs, generative adversarial networks or GANs, diffusion models like Stable Diffusion and DALL-E, or transformer models. These systems typically generate images from text prompts or code rather than manual creation. Human-created images, conversely, are produced by artists using traditional media such as pencils and paint, or computer tools like Photoshop, cameras, or specialized applications. These require manual labor, artistic skills, and often physical materials. The key difference is speed and scale. AI can produce thousands of images within minutes, while human-created artwork requires time, effort, and genuine creative vision. Sample images and dataset. Our implementation utilizes several state-of-the-art CNN models, including ResNet 50, ResNet 152 v2, ResNet 50 v2, Inception v3, Conception, EfficientNet v3, and EfficientNet v5. The dataset comes from the Kaggle repository titled AIV's Human-Generated Images. As you can see in our sample image grid, we have a diverse collection spanning various subjects, from interior design and portraits to landscapes and architectural photography. Each image is carefully labeled as either AI-generated or human-created, providing our models with clear learning targets. Comprehensive literature review. Our literature review encompasses 10 key research papers from 2021 to 2025, demonstrating the rapid evolution in this field. Notable findings include ResNet 50 achieving over 80% accuracy on the Warwick QU dataset in 2021, while recent 2025 studies show EfficientNet v2b2 reaching near perfect 99.9% accuracy on balanced datasets. The research reveals interesting patterns. EfficientNet variants consistently outperform other architectures. Conception excels in deepfake detection scenarios, and transfer learning significantly improves performance across all models. However, most studies highlight limitations including small dataset sizes, limited generalizability, and the need for better real-time processing capabilities. System architecture. Our block diagram illustrates a straightforward yet powerful workflow. Input images flow through preprocessing, which includes resizing and normalization. The processed data then enters our neural network training phase, followed by classification, and finally produces output results, either AI-generated or human-created labels. Our flow diagram shows the decision-making process. Starting with input data, we proceed through preprocessing, then enter an iterative training loop. The system checks for model convergence, and if not achieved, continues training. Once converged, we move to classification, which determines whether the result indicates AI generation or human creation. Technical implementation. Our technical stack relies on Python for programming, Google Colab for development and training, and Kaggle for data storage and access. This combination provides us with powerful computational resources and seamless data management capabilities. The implementation begins by mounting Google Drive for data access, followed by extracting ZIP files containing our training and test images. We import essential libraries including OpenCV for image processing, NumPy and Pandas for data manipulation, TensorFlow and Keras for deep learning, and Plotly with Matplotlib for comprehensive visualization. Our data preprocessing pipeline reads images with OpenCV, converts from BGR to RGB color space, resizes all images to 512 by 512 pixels, and normalizes pixel values between 0 and 1. We create efficient TensorFlow datasets with proper batching and prefetching for optimal training performance. Model architecture and training. We instantiate pre-trained backbones without their original classification heads, freeze their weights to preserve learned ImageNet features, and attach custom classification heads. These heads include global average pooling layers, dropout for regularization, and dense layers culminating in sigmoid activation for binary classification. Our training process employs binary cross-entropy loss, atom optimization, and tracks comprehensive metrics including accuracy, precision, and recall. We implement robust callbacks for early stopping, model checkpointing, CSV logging, and NaN termination to ensure reliable training. Results and visualization. Our class distribution analysis confirms a perfectly balanced dataset with exactly 50% AI-generated and 50% human-created images, 39,975 samples in each category. This balance is crucial for preventing bias and ensuring fair model evaluation. Training data comprises 63,960 images, testing uses 7,995 images, and validation employs. Our research is built upon a solid foundation of academic literature. We have compiled 14 comprehensive references spanning from 2021 to 2025, demonstrating the rapid evolution and current state of AI-generated image detection research. These references include studies on ResNet architectures, EfficientNet variants, transfer learning applications, and comparative analyses of CNN models for image classification tasks. The literature encompasses work from leading conferences and journals in computer vision, artificial intelligence, and digital forensics. Now that we've established our theoretical foundation through this extensive literature review, let me proceed to demonstrate our practical implementation by running the actual code that brings our methodology to life.